Hey, what's up, guys? Yeah, so today, so previously, we already talked about the solvable groups and the Galois group. So the idea is basically, so in the group theory, we know that the Sn is not solvable. So basically, for n greater or equal to 5. Okay, so immediately there's a question that is there is really a polynomial such that whose Galois group is S5, right? So the question is that how can one find a polynomial, let's say polynomial in a rational coefficient such that its Galois group is indeed S5. Okay, so previously we didn't give the proof for this, and we didn't give you the example. So naively, maybe you will think, oh, sure, this is true, right? So Galois group should be arbitrarily large. If you hand me the degree 5 polynomials, then the Galois group of this polynomial should be S5, right? But this is not so easy to construct. Okay, so this is our purpose for this video, that I will give you the example, and I will give you the general recipe that in what sense that you can get this kind of Galois group. Okay, so theorem. This theorem is we are going to prove it. It's basically said that the Q of X, suppose Q of X is irreducible, and degree P, where P is prime. Okay, and let's say Q of X is a rational polynomial, and Q of X has exactly two non-real roots. Okay, so basically they are conjugate to each other, right? Because the rational Q, so has two non-zero tertiary, has two non-real roots. Then the Galois of Q over Q will be SP. Okay, so this is a very good example, a very good theorem. For example, you can define Q of X to be 2x to the 5 minus 10x plus 5. And then you can use your calculus to draw like this, right? So you can check, which proves that the Galois group of this Q as Q will be S5. So this polynomial cannot solve by radicals. Okay, so let's see a proof. So proof will involve will involve some results, and by finally we need to use some group theory to massage it. Okay, so let's prove. So idea is that we know, let's say alpha is the roots, right? So let's say alpha is the roots of this Q of X, and we know that the Galois group, let's say K is the splitting field. K is splitting field of Q. So I know that K over Q is the same as K over Q alpha at joint alpha, and Q alpha at joint Q. Okay. And then this is P, right? Because this is degree P polynomials. So P times something, which prove that P divides K over Q. Okay. So which means that this Galois group has order P divides it, right? So by Cauchy's theorem, so this is the group theory. By Cauchy's theorem, there is a order P. There is an element with order P. Okay. Okay, so this is the first result. And the second, okay, so the second result is basically we get the complex conjugate, right? So I can define tau to A plus BI mapped to A minus BI. Okay, so but we have only two non-real roots, right? So that means they must exchange with each other, right? So tau is belongs to this Galois group Q over Q, and then let's say tau will exchange. So tau exchange two. Tau must induce operations and induce action on Galois group by exchanging two roots, two non-real roots. Okay, so we have these two results. So in terms of the subgroups of, so we know that the Galois Q over Q is a subgroup of SP. Okay, so by 1, we know that there is a element of order P. Okay, but in the group theory, we know that, okay, so fact. So we know that there's only one kind of element in SP has order P, which is indeed a P cycle. So basically, you can reformulate S into you can reformulate 0, 1, 2 up to P minus 1. Okay, so I can relabel the roots such that they call 0, 2, or 0, 1, 2 up to P minus 1. Okay, and this proof is very simple, right? Because P is prime. So for example, let's say S5, right? If you get 1, 2, 3, 4, 5, and this order is 3, right? This order is 2. Right, so total order is 6, right? So, but this is 5. So there's no way that there's only one possibility is that in SP, your element has order P. This must be a P cycle, okay? And I can reorder it to be 0, 1 up to P minus 1. Okay, so and the tau will be a transposition, right? So a tau can be transposition by any two elements. Let's say, so maybe in this case, let's say AB. Okay, so we know that let's say this is C. So we know that our Galois group at least contains two elements. One is this P cycle, and the one is this transposition. Okay, so the Galois theory is finished. So the fact is the group theory. Okay, so lemma. Basically, the P cycle plus transposition, any two transposition, give you what? Give you all SP. So basically, SP is generated by any P cycles and any two transposition. Okay, so this is just a simple, probably not so simple, but a simple group results. Okay, so let's give the proof. So let's talk about the shortcut. Okay, the shortcut is what? The shortcut is that let's talking about the shortcut. Okay, so let's prove. So suppose your C is basically 0, 1 up to let's say P minus 1, and then let's say I can reorder it like this, and I can say that I can define tau to be, let's say, 0 and A. Okay, because I can relabel the first two non-zero roots, not non-real roots, to be 0, and make the A to be the something, and I relabel it to 0, 1, 2, 2, P minus 1, and 0, A. Okay. So simple calculation is that you can check, let's say you check C inverse and the tau act on C, and you can, I think this will be, let's check it, right? So you get P minus 1, P minus 2, to 0, and 0, A, and 0, 1, 2, to P minus 1. So let's check, right? Suppose this is 1. Let's check where 1 goes from, right? So let's say this is A plus 1, this is A. So A plus 1 go to A go to 0, 0 go to 1, right? So A plus 1 go to 1, and then you can check that you know it's order 2, right? So A plus 1 go to 1, 1 must go to A plus 1, right? So you can shift 1, right? You can shift 1. So basically, you can check that if you go to C minus tau C again, then you can get, like, I think 2A plus 2. Okay, so basically from this you can get 0A, 0, 2A, 0, 3A. Okay. Really? Let's see. Sorry. You can get 0A and A, 2A, and 2A, 3A by adding a constant, right? So basically you can get KA plus K. Okay, so you can get A. We can start from the 0A, right? Go to A, 2A, go to 2A, 3A. And then we know that in the prime power, in the prime, right? Because P is prime, so AB, there is a B such that AB equals to 1. Right, so you can get like B minus 1A and A. Okay, so you can start from 0A, and you see that let's see. So if somebody give you 0A and A2A and 0A, you can check that 0 go to A. Sorry, 0 go to A, go to 2A. Right, so 0 go to 2A. Right, so basically you can get 0A, 0 2A, 0 3A, but you keep iterating. Right, so you finally you get 0BA, where 0 1. Okay. So which which we prove that this Galois group Q has p cycle 0, 1 to 2 up to p minus 1 and 0, 1. Okay, so then it's very standard results in the group theory that you can start from this and construct your full symmetric group SP. Okay, so let me just quickly prove it. So now the rest is trivial. You can check that if you define if you let's say this is C, and let's say this is B. So suppose you can check that if you do the CBC inverse, then you get 1 2. Okay, and then you get if you do CKB C inverse K, you get K plus 1, K plus 2. So you can get 0 1 1 2 up to P minus 1, P minus 2. Okay, once you have this, then let's say you get any transposition X and Y, you can get X plus 1, X plus 1, X plus 2, and up to 1 minus 1Y. Right, so this is just the iterative. You change one by one. And then this is in generated by this, degenerated generated this. So we will prove that any transpositions generated can be generated forced into this Galois group, and all the SP are generated by any two transpositions, a composition of two transpositions. Okay, so we prove that in this case that your Galois group is in DSP. And then more generally, you can try to construct. So for actually, one can prove that for any n degree n rational number, rational polynomial irreducible, you can always find such polynomial with the Galois group Sn. But this is much more difficult results. But in a prime number, we got simple results. Okay, so this is why one can construct a Galois group with the order SP, which we prove that for any prime power. So basically, we prove that for any prime. So for any prime number, P, there is a polynomial P of X, Q of X, such that the Galois group of this P is indeed SP. Basically, it's not solvable. P greater or equal to 5. Okay, see you guys next videos.